The following presentation was produced by the Clemson University Cooperative Extension Service through funding by the Southern Regional Aquaculture Center, United States Department of Agriculture, and the U.S. Fish and Wildlife Service, United States Department of the Interior.
Successful fish production is dependent on the quality of water present. As mentioned in Tape 1 of this series, a pond with good water quality will produce more fish than a pond with poor water quality. To ensure production of healthy fish, we must manage water quality. However, before proper water quality management occurs, one must have a basic knowledge of individual water quality conditions and how they interact to affect the overall biology of the pond. The purpose of this tape is to discuss several water quality characteristics that have been proven to be critical in fish production operations and to help provide a working knowledge of factors influencing the overall biology of the pond. Testing procedures and corrective measures for the parameters discussed in this tape will be described in Tape 3 of this series. Plankton is comprised of all microscopic organisms which are suspended in water, such as bacteria, small animals or zooplankton, small plants, or phytoplankton. The green tint of this water is due to chlorophyll of thousands of phytoplanktonic organisms. Pond water which is colored such as this is said to have a bloom of phytoplankton or algae. Some types of phytoplankton grow in colonies which often form scums on surface. Since phytoplankton is interrelated to virtually every factor in the pond ecosystem, the importance of plankton to the overall biology of the pond cannot be underestimated. Planktonic organisms form the base of the food chain or food web in ponds. For example, in a typical bass pond, plankton are interrelated in the food web. As shown in this diagram, phytoplankton are consumed by zooplankton. Zooplankton in turn are consumed by insects and juvenile sunfish and bass. Insects are consumed by sunfish and bass, and sunfish and small bass are eaten by large bass. All dead organisms, including phytoplankton and zooplankton, form detritus, an organic material, as they decay. Detritus contains many nutrients, such as minerals, which are recycled back into the food web by zooplankton and insects which feed upon it. Shown here is the food web present in a typical catfish pond. In this type of pond, planktonic organisms are less important as food sources since the fish are artificially fed. However, nutrient recycling by plankton in this case is important. Most production ponds which are fed have food webs such as this. In both fed and unfed ponds, phytoplankton influence overall water quality. Phytoplankton influences the level of dissolved oxygen, pH, and nitrogen. Specific examples of how phytoplankton is involved with these parameters will be included as they are discussed. Phytoplankton also aids in the prevention of large aquatic plant growth. This is due to the shading effect, which is caused by phytoplankton. Shading by phytoplankton prevents sufficient light from reaching the larger plants, which in turn inhibits their growth. Dense growth of aquatic plants is undesirable as it inhibits fishing and seining and also can produce increased oxygen demand in the pond. Phytoplankton, like all green plants, utilize the process of photosynthesis in which carbon dioxide and water are converted to oxygen and carbohydrate by using sunlight as an energy source. By this process, phytoplankton produces its own food, which are sugars. Enough available carbon is necessary for healthy algae. However, additional nutrients besides carbon dioxide and water are necessary for growth of phytoplankton. The limiting factors to phytoplanktonic growth besides adequate sunlight are usually nitrogen, phosphorus, and potassium, or NPK. Of these, phosphorus is usually limiting, and the lack of this nutrient will cause reduced growth. Many trace minerals have been shown to affect planktonic growth, but these are usually not the limiting factors. In many cases, fertilization is needed to establish a phytoplankton community. Fertilizers provide these limiting nutrients. For example, the standard fish pond fertilizer contains 20% nitrogen, 20% phosphorus, and 5% potassium. Methods of testing the level of phytoplankton in your pond will be presented in Tape 3 along with fertilization information. Plankton communities are constantly changing in species composition and in abundance. For example, fluctuations in abundance are shown in this graph of chlorophyll A concentrations. As numbers of phytoplankton increase, the quantity of chlorophyll A increases. As shown in this graph, phytoplankton abundance reach maximum levels in the late summer months. Increased sunlight and warmer temperatures promote this increase in growth. Fertilizer also increases growth, as is shown. Even though phytoplankton abundance may vary greatly through the year, fish production usually is not affected. However, during the warmer months, phytoplankton blooms may increase greatly in density and then suddenly die. If this occurs, several problems involving oxygen concentrations may result. This subject will be discussed later in the video when we discuss dissolved oxygen. At certain times of the year, certain types of plankton, the most notable being blue-green algae, may increase in abundance. These forms of plankton produce certain substances which may cause off flavor in fish. At the present time, there is no reliable method for predicting when off flavor will occur or its duration. Before proceeding to the next topic, let me emphasize again the importance of phytoplankton to fish production. The most important aspect of water quality management is management of phytoplankton due to its importance in the food web, nutrient recycling, aquatic plant control, and effects it has on the following parameters: dissolved oxygen, pH, and nitrogen. Maintaining adequate concentrations of dissolved oxygen is critical to successful fish production. Adequate dissolved oxygen is necessary not only to prevent massive fish kills, but also to maintain healthy growing fish. Generally, it is desirable to maintain dissolved oxygen levels above 5 milligrams per liter. Prolonged exposure to dissolved oxygen concentrations from 1 to 5 milligrams per liter usually causes reduced growth and increases the susceptibility of fish to disease. Values below 1 milligram per liter are usually lethal to most fish if exposure is prolonged. Although the atmosphere is 21% oxygen by volume, this oxygen is not directly available to fish unless it is dissolved into the water. Water has a specific capacity to hold dissolved oxygen, which is regulated by several physical parameters. When the amount of dissolved oxygen in water is equal to that of the air it is in contact with, the water is saturated. Temperature, atmospheric pressure, and salinity are the major parameters which influence the amount of oxygen that can be dissolved in water. In the southern United States, temperature has the greatest effect on the amount of dissolved oxygen at saturation. For example, one can see that as temperature increases, the amount of oxygen at saturation decreases. In the summer, as water temperatures increase significantly, less oxygen can be held by water due to the lower saturation level. This, combined with increased oxygen usage, is the major reason dissolved oxygen deficiencies occur primarily in the summer. The term saturation may be misleading since oxygen levels are constantly changing due to various inputs and outputs. In other words, saturation is simply the maximum amount of oxygen water can retain. But due to several factors, oxygen concentrations vary. Inputs and outputs of dissolved oxygen into and from ponds are primarily from diffusion and photosynthesis and respiration by all living organisms in the pond, especially phytoplankton. Diffusion of oxygen into water occurs whenever the concentration of dissolved oxygen is below saturation. Net diffusion of oxygen also occurs out of water into the air if the concentration of dissolved oxygen in the water exceeds the saturation level. Even though diffusion is constantly occurring, the rate of diffusion is slow and results in small inputs and outputs by this process. For example, in this table, inputs and outputs of dissolved oxygen due to various processes are shown. Diffusion accounts for only a small percentage of both inputs and outputs of oxygen. On the other hand, processes by phytoplankton contribute greatly to both inputs and outputs of dissolved oxygen. Photosynthesis, as you recall, produces oxygen. Respiration, on the other hand, results in oxygen being consumed. All organisms in the pond respire and therefore consume oxygen. The loss of oxygen due to respiration by organisms besides phytoplankton is relatively small when compared to oxygen losses due to respiration of phytoplankton. The process of photosynthesis and respiration by phytoplankton alternate between night and day. That is, photosynthesis requires sunlight and therefore occurs only during the day. At night, photosynthesis ceases and respiration is the dominant process. This results in fluctuations of pond oxygen levels from day to night. As oxygen is produced by photosynthesis during the day, it usually exceeds losses throughout the night due to respiration. If there are no oxygen inputs from photosynthesis, dissolved oxygen drops. From this curve, it can be seen that oxygen levels are greatest shortly before dusk and lowest shortly before dawn. Immediately after dawn, photosynthesis begins and oxygen levels increase. Deviations from this normal dissolved oxygen curve may be caused by increased diffusion, plankton die-offs, pond mixing, and decreased photosynthesis due to cloudy weather. Diffusion may increase or decrease dissolved oxygen concentrations depending on the saturation level of the pond. Wave action caused by wind exposes more water to the air, increasing the rate of diffusion. In fact, corrective measures for low dissolved oxygen are based on this principle. For example, aeration devices such as this are used to expose water to the air, thereby increasing diffusion of oxygen, in this case into the water. Sudden die-offs of phytoplankton may occur at times. When a die-off occurs, dead algae may form near the surface. As plankton dies, photosynthesis ceases and respiration increases due to microbial decomposition, and as a result, dissolved oxygen concentrations fall dramatically. As shown in this graph, dissolved oxygen concentrations suddenly dropped immediately after the die-off of plankton and remain low for several days because of increased respiration and decreased photosynthesis. Die-offs of phytoplankton usually occur during the warmer months during calm weather. If corrective measures are not immediately taken following a die-off, a massive fish kill may result. Fish kills may result from extremely windy weather or heavy rains, which may cause turnover or mixing of low oxygen bottom waters with those throughout the pond, resulting in reduced oxygen concentrations. Cloudy weather will also result in decreased oxygen concentrations due to reduced photosynthesis by phytoplankton. As shown in the graph, as cloudy weather persists for several days, dissolved oxygen concentrations decrease. pH is a measure of the hydrogen ion concentration and indicates if the water is acid or basic. Since pH represents a negative log of the hydrogen ion concentration, the lower the pH, the greater the number of hydrogen ions. The higher the pH, the lower the number of hydrogen ions. In other words, as hydrogen ion concentration of the water increases, the pH decreases, indicating increased acidity. The pH scale ranges from 0 to 14, with 7 being neutral. Water with values below 7 are termed acidic. Those with values above 7 are basic or alkaline. The greater the departure from pH 7, the more acid or alkaline a water is. For example, water with a pH of 5 is more acidic than water with a pH of 6 and has more hydrogen ions. The pH of a pond is directly influenced by the concentration of carbon dioxide in the water. Carbon dioxide, in turn, is directly influenced by phytoplankton and other organisms in the pond. During the day, removal of carbon dioxide by photosynthesis of phytoplankton causes the pH to rise. At night, addition of carbon dioxide to the water by respiration of phytoplankton and other organisms decreases the pH. This results in a fluctuation of both pH and carbon dioxide over a 24-hour period, as shown in this graph. Carbon dioxide influences pH due to its direct effects as an acid and its relationship with the bicarbonate equilibrium system. At night, respiratory carbon dioxide causes the pH to decrease because carbon dioxide in water acts as an acid in the reaction shown. Increased carbon dioxide causes the reaction to shift to the right, producing hydrogen ions. Recall that increased free hydrogen ion concentrations result in decreased pH. In the daylight hours, carbon dioxide is removed by photosynthesis. This causes bicarbonate ions to dissociate and replace the decreasing carbon dioxide concentrations. In other words, the reaction shifts to the right. This shift produces increased concentrations of carbonate ions. As carbonate ions are formed, they are hydrolyzed, which increases the concentration of hydroxide ions, which increase the pH. In summary, the extent of pH fluctuations in ponds depends on the amount of carbon dioxide removed or added by photosynthesis and respiration and the total alkalinity and total hardness of the water. Total alkalinity and total hardness form a buffer system in which the excess hydrogen and hydroxide ions formed by addition or removal of carbon dioxide are taken out of the system. That is, they are bound with other compounds. Total alkalinity and total hardness were discussed in detail in Tape 1 of this series. Fish are sensitive to extreme values of pH. The acidic and basic death points for most fish are approximately pH 4 and 11 respectively. However, slow growth may occur in moderately acidic or basic waters. In waters which are not buffered sufficiently, the pH may remain at these values for long periods of time, thereby inhibiting growth. In properly buffered ponds, the pH will remain between approximately pH 6 and 9 most of the time. This range is desirable for fish production. The pH of a pond also influences the toxicity of other compounds such as hydrogen sulfide and ammonia. The toxicity of hydrogen sulfide, which was discussed in Tape 1, increases as pH decreases, whereas the toxicity of ammonia increases as pH increases. The effects of pH on ammonia toxicity will be discussed in detail later in the video. pH also affects the toxicity of certain treatments such as copper sulfate, as low pH makes copper more toxic. Consult your county extension agent or aquaculture specialist before treatments. Nitrogen is an essential element for all living organisms because it is contained in protein. However, two forms of nitrogen commonly found in ponds, unionized ammonia and nitrite, are toxic to fish at relatively low concentrations. Nitrogen in ponds exists in many different compounds which collectively form the nitrogen cycle. Inputs of nitrogen are from fixation of atmospheric nitrogen by some algae and bacteria, fertilizer runoff into the pond, and from feed in ponds which are fed. In fact, this is the largest source of nitrogen in fed ponds. As nitrogen-containing proteins in the feed are digested by fish, ammonia is produced. Ammonia is the nitrogenous waste product of fish and other aquatic animals. Ammonia may be lost to the atmosphere or may be assimilated by plants and phytoplankton, or nitrified to nitrate with nitrite as an intermediate product. Nitrate can also be assimilated by plants and phytoplankton. Nitrification occurs in two steps. Step 1 results in ammonia being converted to nitrite by the action of Nitrosomonas bacteria. Step 2 results in nitrite being converted to nitrate by Nitrobacter bacteria. Denitrification occurs under anaerobic conditions, that is, without oxygen, resulting in nitrate being converted to nitrite, then nitrogen gas, which is lost to the atmosphere. Because ammonia is the major end product of protein digestion in fish, it is excreted primarily as unionized ammonia from the gills. Ammonia concentrations increase as stocking density increases and also as feeding rates are increased. Ammonia exists in two forms in pond water, the unionized and the ionized form. Increasing pH and temperature shifts this reaction to the right. For example, one can see that there is a much greater percentage of ammonia in the unionized form at pH 8 than at pH 7. pH affects the percentage of unionized ammonia much more than temperature. The unionized form of ammonia is much more toxic to fish than the ionized form. Unionized ammonia concentrations in most ponds range from 0 to 1 milligram per liter. Since pH directly influences the amount of unionized ammonia, this compound fluctuates during a 24-hour period, with highest values in the afternoon when pH is greatest. Seasonal fluctuations in ammonia also exist. These are due mainly to the activities of phytoplankton. Phytoplankton influences ammonia concentrations by assimilating or taking up ammonia. Therefore, when phytoplankton are abundant, less ammonia is present. On the other hand, when phytoplankton are less abundant, ammonia increases. As a result, concentrations of ammonia often remain quite high in the winter due to decreased phytoplankton abundance. High ammonia may also result from die-offs of phytoplankton in which the nitrogen contained in these organisms are released as ammonia. The toxicity of unionized ammonia to fish varies greatly from species to species, with toxic values ranging from approximately 0.5 to 2 milligrams per liter. However, sublethal values have been shown to reduce growth and induce stress. High concentrations of nitrite in ponds usually occur when the water is relatively cool in the spring and fall. The accumulation of nitrite in ponds is due primarily to the breakdown of the nitrification process. Recall that nitrification results in ammonia being converted first to nitrite, then to nitrate. Also recall that two different bacteria are responsible for these steps. The bacteria Nitrosomonas, which converts ammonia to nitrite, is tolerant to wide fluctuations in temperature, whereas Nitrobacter, which converts nitrite to nitrate, grows best in warmer temperatures. Therefore, in the absence of Nitrobacter activity, nitrite concentrations may increase considerably. Since Nitrobacter grow best in warm water, their absence in the cooler months usually translates to increased nitrite concentrations. Also, increases in nitrite usually follow increases in ammonia concentrations. Toxicity of nitrite increases as pH decreases due to the formation of nitrous acid. In the presence of decreased pH, the reaction shifts to the left and more nitrous acid is formed. Fish are highly susceptible to nitrite. Lethal values are extremely variable and are influenced primarily by the chloride concentration of the pond. Generally, a 3:1 to 5:1 chloride to nitrite ratio will protect fish from the adverse effects of nitrite toxicity. Fish are evidently unable to distinguish chloride from nitrite, and by increasing the chloride ion concentration, fewer nitrite ions get into the fish. Fish exposed to nitrite lose the ability to carry oxygen in their blood due to nitrite's effects on hemoglobin. This causes methemoglobinemia, a form of anemia. This results in the blood turning a brownish color. This is why nitrite toxicity is often called brown blood disease. The tubes shown here contain diluted samples of blood from fish exposed to various concentrations of nitrite. The second tube from the right contains blood from an unexposed fish. Nitrite toxicity is more of a problem in holding tanks and recirculating systems than in ponds. This is due primarily to higher densities of fish and a subsequent buildup of nitrogen. Remember that proper management of water quality is the key to successful fish production. In this tape, several important water quality parameters have been discussed. In some instances, however, fish health may be jeopardized by other factors. If you have a problem you cannot solve or are unsure about your water quality, contact your county extension agent or aquaculture specialist. Tape 3 will describe testing methods and corrective measures for the parameters discussed in this tape. Plankton is comprised of all microscopic organisms which are suspended in water, such as bacteria, small animals or zooplankton, small plants, or phytoplankton. The green tint of this water is due to chlorophyll of thousands of phytoplanktonic organisms. Pond water which is colored such as this is said to have a bloom of phytoplankton or algae. Some types of phytoplankton grow in colonies which often form scums on surface. Since phytoplankton is interrelated to virtually every factor in the pond ecosystem, the importance of plankton to the overall biology of the pond cannot be underestimated. Planktonic organisms form the base feed upon it. Shown here is the food web present in a typical catfish pond. In this type of pond, planktonic organisms are less important as food sources since the fish are artificially fed. However, nutrient recycling by plankton in this case is important. Most production ponds which are fed have food webs such as this. In both fed and unfed ponds, phytoplankton influence overall water quality. Phytoplankton influences the level of dissolved oxygen, pH, and nitrogen. Specific examples of how phytoplankton is involved with these parameters will be included as they are discussed. Of the food chain or food web in ponds. For example, in a typical bass pond, plankton are interrelated in the food web. As shown in this diagram, phytoplankton are consumed by zooplankton. Zooplankton in turn are consumed by insects and juvenile sunfish and bass. Insects are consumed by sunfish and bass, and sunfish and small bass are eaten by large bass. All dead organisms, including phytoplankton and zooplankton, form detritus, an organic material, as they decay. Detritus contains many nutrients, such as minerals, which are recycled back into the food web by zooplankton, and insects, which...
The following presentation was produced by the Clemson University Cooperative Extension Service through funding by the Southern Regional Aquaculture Center, United States Department of Agriculture, and the U.S. Fish and Wildlife Service, United States Department of the Interior.
Successful fish production is dependent on the quality of water present. As mentioned in Tape 1 of this series, a pond with good water quality will produce more fish than a pond with poor water quality. To ensure production of healthy fish, we must manage water quality. However, before proper water quality management occurs, one must have a basic knowledge of individual water quality conditions and how they interact to affect the overall biology of the pond. The purpose of this tape is to to discuss several water quality characteristics that have been proven to be critical in fish production operations and to help provide a working knowledge of factors influencing the overall biology of the pond. Testing procedures and corrective measures for the parameters discussed in this tape will be described in Tape 3 of this series.